Hey guys, it's Miss Maneely, and I'm going to go through your probability review packet to help prepare for Tuesday's test. The first question says the probability that it will thunderstorm today is 80%, and the probability that it will thunderstorm tomorrow is 30%. The probability that it will thunderstorm both days is 15%. What is the probability that it will thunderstorm today or tomorrow? There are a couple different ways that you can do this problem. When you see the or statement, and you're given like two different probabilities and you know they overlap because we know that there's a both, one thing that you can do is draw a Venn diagram. And I do think sometimes drawing a picture helps understand a situation. So if we draw a Venn diagram, I'm going to have one circle that represents thunderstorm today. And then I'm going to have another circle that represents the thunderstorm tomorrow. And I'm just going to abbreviate that. The trick with it's not really a trick, but the thing you have to pay attention to with the Venn diagram is that the probability that it'll thunderstorm today is going to encompass this whole entire circle. And then the place where they overlap is where it thunderstorms today and tomorrow. And you got to be careful to subtract away the overlap from each of the individual probabilities. So for example, I know that the probability that it'll thunderstorm today is 80%. So I know this whole circle has to add up to 80%. But I don't want to put in the 80% quite yet because I know that it's going to thunderstorm on both days 15% of the time. So I want to plug in my overlap first. So if I plug that in, and I know that the whole circle for today has to add up to 80, if I take my 80%, and subtract away the 15, then I know 65% of the time it'll rain only today and not tomorrow. And I have to do the same thing with the likelihood of I'm saying rain, but a thunderstorm tomorrow. We know that the probability that that'll happen is 30%. Well, if I know, so 30% needs to be the total for this whole circle. Well, I know that 15% of the time it rains both days, so I need to subtract away that 15%, and that means that it's going to rain tomorrow and not today 15% of the time. I can also figure out the area on the outside if I wanted to complete the Venn diagram, because if I take my 65% and I add that to my 15%, and then I add that to my other 15%, that gives me a total of 95%. And so I know that a complete probability model has to add up to 1, so that means I'd have 5% of the time it wouldn't thunderstorm on either day. But the question that I'm trying to answer is, what is the probability that it will thunderstorm today or tomorrow? So the probability that it's going to thunderstorm today or tomorrow. If I use my Venn diagram, remember that the or corresponds to a union, and that means it could be anywhere in this area here, anywhere inside either one of these circles or both. And so I already actually did the calculation. It's 65 plus 15 plus 15, which means 95% of the time it's going to rain on either day. Another way you could do this would be using the probability formula, the general addition rule, but I actually think that sometimes that confuses people. The general addition rule basically says if we have the probability of A or B, that's simply going to be the probability of A plus the probability of B minus the probability of both, and that would be A and B. And so if we think of A as being thunderstorm today and B representing thunderstorming tomorrow, then I can just use the probabilities in the problem because I know the probability that it'll thunderstorm today is 80%. I know the probability that it'll thunderstorm tomorrow is 30%. And when I add the two probabilities, I'm adding the overlap twice. So I have to subtract it away, which means I'd have to subtract the probability of both days, which is 15. And if you compute this expression, so 0.8 plus 0.3 minus 0.15, you'll notice you get the same answer. So it doesn't matter which way you do it. If you understand the Venn diagram, then please use the Venn diagram. It is a little bit more work, but I think sometimes students have a tendency to mix the Venn diagram and the formula up. So choose one method or the other that works for you. In number 2, it says on a football team, the probability of throwing left-handed is 50% and the probability of kicking left-footed is 4%. If the probability of throwing left-handed or kicking left-footed is 14%, what is the probability of both? Now in this problem, you're given the or and you're asked to find the and. And so I'm actually going to need to use my probability rule here. But let's just outline what information is given. So on a football team, we know the probability of throwing left-handed. So the probability of throwing, I'm just going to call that T, is 50%. And the probability of kicking left-footed is 4%. Make sure you change these to a decimal, and 4% is 0.04. You have to move the decimal back 2 units. And then we're told the probability of throwing left-handed or kicking, so the probability of throwing or kicking is equal to 14%, and I need to find the probability of both. Well, if I plug these values into my probability rule, and I just let T correspond to A and K correspond to B, then I know if I'm looking at my OR statement, that's going to correspond to my 0.14, and that has to equal the probability of my A, which would be the probability of T, and that's going to be 0.5, plus the probability of B, which I'm associating with K, that's going to be 0.04, and I need to subtract the probability of both. Well, this is what I don't know, so let's just call that X. Now I have a linear equation. To solve my linear equation, I'm going to want to simplify both sides. So if I put those two together, I have 0.14 is equal to 0.54 minus x. There are a couple different ways you can solve for x, but if I subtract 54% from both sides, 14 minus 54 is going to give me a negative 40% is equal to a negative x. And at this point, if I have a negative number equals another negative number, if I divide by -1, I find that x is equal to 0.4. So that means the probability of being able to throw left-handed and kick left-handed is going to be 40%. You could do this using a Venn diagram, but the math is the same. Since you don't know the overlap, it's going to be hard to compute using a Venn diagram. So in this case, it actually is a lot easier to use the general addition rule. Remember, OR corresponds with addition and corresponds with multiplication. But you have to pay attention because with the OR statement, you have to think about whether or not the events are disjoint, whether or not there's an overlap. With the AND statement, you need to pay attention as to whether or not the events are independent. And in this case, in both of these cases, there's an overlap, so I know that the events are not disjoint. Okay, number 3, we had a problem like this on our quiz. It says to look at the image of the combination lock below. Each dial contains the digits 0 through 9. That means that there's 10 digits. If you count 0, that's the first digit. 9 would be the 10th digit. The proper combination of 5 digits will release the lock. Suppose you don't know the correct combination, so you randomly select digits. What is the probability of selecting the correct combination on the first try? Well, you have to think, well, how many combinations are correct? So the probability of selecting the correct combination on the first try. Well, there's only one correct combination, so that's going to be my numerator. I also have to think about all of the other possible combinations. This is where we have to use our multiplication principle. This is where I think, okay, on that first dial, there's 10 outcomes. On the second dial, there's 10 outcomes. On the third, there's 10. Another 10, another 10. So if I do this on my calculator, this is the same thing. If you don't want to multiply 10 by itself 5 times, you can say this is 10 to the 5th power. And 10 to the 5th power is actually just going to be a 1 with 5 zeros. So that's what, 100,000? And so if I'm finding the probability would be 1 out of 100,000. If you wanted to divide, you could, but you can just leave it as a fraction. In number 4, you're asked which of the following is a legitimate probability distribution and why. There's 2 criteria for a probability distribution. First of all probabilities have to be between 0 and 1. And the sum of all the probabilities, oops, I spelled that wrong. The sum of all of our probabilities has to add up to 1. So if I take a look at letter A, notice how the event 1 has a probability of negative 0.08. That's not possible. So it's not possible to have a negative probability. And so this would be not legitimate. If I take a look at letter B, notice that all my probabilities are between 0 and 1. So that's met. So that's met. The other thing I want to do is check to make sure that when I add them together, it equals 1. So if I had 0.06 plus 0.28 to 1.5 and 0.3 and 0.21, I get 1. So this is a legitimate probability model. All right, let's take a look at number 5. Here we have a two-way table. And so we're going to use this information to answer questions 5 and 6. So we're given information about we know that there are 400 randomly selected students. So I know right here that the total is 400. That's really helpful to me. And it has to do with what class they're in and then their favorite sport. So number 5, it says, what's the probability of selecting a student at random who is a junior? As soon as it tells me something like that, this becomes given information. Oh, no, it's not. Sorry, I wrote this wrong. Forget what I just said. Let's finish reading the question. So what is the probability of selecting a student at random who is a junior given the student would choose football as their favorite sport? Okay, here you're actually told what the given information is. So remember, when we're dealing with a given statement, we're dealing with a conditional probability. And the condition always comes second in the statement. So if I'm given that the favorite sport is football, that's going to be here or here. So it's always going to come next. It's always going to come after the vertical line. So I know that it can't be C or D. I can eliminate those options right away. Now I want to know the probability that the student is a junior. So remember, whatever is my given, that's what I'm going to be dividing by. So if I know that the student is a junior, I'm not talking about all 400 students. I'm sorry, if I know the student plays football or likes football, I'm not talking about everybody, I'm just talking about the students who like football. So I need to find that total. So 37 plus 19 plus 7 plus 24 is actually equal to 87. And so that's got to be what I divide by. If I want to know the likelihood that they're also a junior, that's going to correspond to the 7. So my fraction is simply 7 over 87, and that would be letter B. Number 6 says, are the events junior and choosing football as the homecoming theme independent? Use mathematics to justify your answer. The easiest way to do this, if you remember, we said if the probability of A given B is still equal to the probability of A, then A and B are independent. And so if I think about it, I just found out that the probability of junior given football is 7 out of 87. So basically, if I can show that this is also equal to the probability of choosing a junior, and if I can show that those two probabilities are the same, then I can conclude that these two events are independent. So let's find the probability of selecting a junior. I've got to figure out how many juniors there are. So let's add them up. We've got 29. Oops. 29 plus 7 plus 3 plus 61. And that gives me 100. And if I'm choosing a junior, I'm choosing them out of the whole group, and so that denominator is going to be the 400 people in my sample. And 100 out of 400 is actually going to be 0.25. And if I double check in the other fraction, 7 over 87, if I reduce that to a decimal, and I get 0.08. And so what I'd want to say, and you're going to want to write this out. This is kind of like a proof in geometry. So what I'd want to say is since the probability of j given f is not the same as the probability of j, the events are not independent. Okay. If those two probabilities were the same, then I could say the two events are independent. I could also look at the probability of junior, the probability of football, and the probability of both and see if when I multiply the probability of junior times the probability of football, I get the probability of both. But since we already have this probability and we'd only need to find one more, this is the easier way to show independence. Okay. Number 7, it says a local golf shop sells blue and gold golf balls at a school fundraiser. Suppose 55% of the golf balls are blue. Suppose further that 10% of the blue golf balls and 15% of the gold golf balls are used. It says to construct a tree diagram to illustrate the possible outcomes. So we've got to think, if it's a tree diagram, that means there are stages to this situation. So we got to think about which stage is going to come first, the color or whether or not they're used. So if you think about the way the statement is written, where it says 10% of the blue golf balls, that means that the blue would be the given. The blue and the gold, the color of the golf ball, is going to be the first stage in our sequence because that's the given, that's the condition. So the golf balls are either blue or gold. And then beyond that, they're either going to be used or new. So once you have the branches developed, we can go back now and assign probabilities. So let's take a look again at that first statement. 55% of the golf balls are blue. So I'm going to write this as a decimal, 55%. Well, if 55% are blue, that means the rest would have to be gold, and the rest would be 45%, because 45 plus 55 gives you 100%. Then if I look at the next statement, I'm going to do this in green. In the next statement, it says, suppose further that of the blue, 10% of the blue are used. And so if I'm looking just at my blue golf balls, I know that 10% are used. That means 90% are not. And then I also know that 15% of the gold golf balls are used. So I'm going to put my 15% here. That means that the gold golf balls, 15% are used. That means 85% of them are new. And this is how you would set up your tree diagram. So you want to make sure you label all the outcomes and all the probabilities. So if I want to know the probability that a randomly selected golf ball is used, I've got to think about all the different ways that could happen. And if you think about it, I could choose a blue golf ball that is used, or I could get a gold golf ball that is used. And so there are two paths I can take. It can be blue and used. So if I were writing this out, you don't have to write this out, but if I were writing it out using notation, I'm going to go ahead and just use B for blue, G for gold, and then U and N for used and new. So I'd be trying to find the probability of blue and used, or gold and used. And remember, with the ands, we multiply. With the ors, we add. So this is basically going to be the probability of blue and used would be 55 times 10, or 55% times 10%, or means I'm going to add the probability that it's gold and used. And that would be 45% times 15%. And if I combine these values, I'm going to have 55 times 0.1 plus 0.45 times 0.15. And that gives me about 0.1225. So about 12.25% of the golf balls are going to be used. Not too bad, so less than 15% altogether. All right, almost done. Number 8 and 9 deal with independence again. So for example, the Thompsons have 3 children, all of whom are boys. They want to have another child. So given that the first 3 children are boys, the probability that the 4th child is a boy would be what? Well, in this case, we know that the gender of children from one child to the next is independent. So just because I've had 3 children who are boys doesn't affect the probability of my 4th child being a boy. So the probability that my 4th child is a boy is going to be 0.5. But look at the next question. This is asked a little bit differently. It's saying, what is the probability of having 4 boys in a row? So in number 8, this is asking me for the probability of having a boy given that I had a boy, boy, boy. And since I have independence, this is the same thing as having the probability of a boy. But in the next one, it's the probability of having 4 boys in a row, which is asking me this: boy, 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 boy. Or if you think about it this way, this is having a boy and having another boy and having another boy and having another boy. So if I think about it using the and statement, then that means I'd have to multiply the probability of having a boy times the probability of having a boy and do that 4 times. Because of independence, I multiply. And I know the probability of having a boy on the first child is 0.5. The probability that my second child is a boy is 0.5. Same with the third, same with the fourth. So this probability is a little bit different. This becomes 0.5 to the 4th power. And when I multiply it all the way out, it becomes 0.0625. So number 8 has to deal with a conditional probability. Number 9 deals with the and statement. All right, last 2 problems. In number 10, it says, suppose that among 5,000 students at a high school, 1,800 are taking a foreign language and 1,500 participate in the drama program. If taking a foreign language and participating in the drama program are independent, that's going to be important, then how many, this is another good question, and a lot of you guys missed this on the quiz that we just took, how many students are taking both a foreign language and participating in the drama program? So let's write down what we know. We know there are 5,000 students total, and I know that 1,800 are taking a foreign language. So the probability of taking a foreign language, I'm just going to call that F, is going to be 1,800 out of 5,000. And the probability, let me do this in a different color, the probability of participating in the drama club would be 1,500 out of 5,000. Since I know that they're independent, that's going to be important, because if I'm looking essentially for the students that are participating in both, then I'm looking for, let's first find the probability of foreign language and drama. Since they're independent, that tells me I can multiply the probability of foreign language times the probability of drama. Well, I have those fractions, right? It's 1,800 out of 5,000 times 1,500 out of 5,000. I'm going to do this on my calculator. Make sure when you're dealing with fractions, you put them in parentheses. So 1,800 divided by 5,000. I'm going to close my parentheses and then multiply by 1,500 divided by 5,000. And I get 0.108. Okay, so that gives me the probability of selecting a student who takes a foreign language and participates in drama. If I want to know how many, which is what the question is asking, then I need to multiply my probability times the number of students at the school. So to answer the question, I need to do 0.108 times 5,000. And so if I do this, I get 540. And make sure you put some units on here. So I'm talking about 540 students that participate in both. In number 11, this is actually one of the easiest ones on here. This goes back to what we did like day 1. To estimate the probability distribution of colors of Jolly Ranchers candies, Miss Smith's class examined the colors in a medium-sized bag of Jolly Ranchers. The frequency table below is displayed. According to the distribution, estimate the probability of randomly selecting a red or a blue. So the probability of red or blue, well, let's think. These are disjoint, right? Because I can't get a blue-red Jolly Rancher. So if it's either blue or red, that means I can add the values together. So there are 16 reds and 18 blues. So 16 plus 18. And I've got to think about the total amount. So in order to calculate the total, I'm going to add them all together. So 16 plus 12 and 19 and 18 and 21. So when I add them all together, I get 86. So the total is 86. And so if I want to find the probability of selecting a red or a blue, I would simply divide that by 86. You could also simply find the probability of red plus the probability of blue. The probability of red would be 16 out of 86. The probability of blue would be 18 out of 86. If you remember your rules for adding fractions, as long as you have a common denominator, you can add the numerators together. And so 16 plus 18 is going to give you 34, I think, out of 86, and that reduces to 0.395. Okay. So hopefully this was helpful. If you have any questions, please come on in to Bulldog Block Friday or Tuesday. Our test is on Tuesday. We'll spend just a few minutes going over the review packet before taking the test. So please come in for extra help if you need it. Good luck.